Can the mean value theorem be applied? Well, this function has one problem, right? At x equals 0, it should be. That is, you want to know if it's continuous and differentiable, right? It's the same conditions, the same first two conditions as Rolle's theorem, only on the given interval. So, is that the case here? Is it continuous on this given interval, the closed interval, differentiable on the open? Well, it's definitely continuous, right? You can plug in any value for f of x. So f is continuous for all real numbers. Right? If you cube, you can cube root any number you want. You can square any number you want. And the combination of those doesn't give you an issue. So the domain's all real numbers, continuous on all real numbers. Differentiable, so if you take a look at the derivative, it would be 2/3 x to the negative 1/3, which is 2 over x to the 1/3. And there you can see you got an issue, right? At x equals, that's a 1/3 in the bottom. You got an issue at x equals 0, okay? So I would say something like this. It's not differentiable at x equals 0, but is on the given interval, okay? So that means we're good to go. So let's find the guaranteed c value such that f prime of c equals the slope of the secant line. So we already have the derivative. I'm going to set that equal to the slope of the secant line. So I got to find the slope of the secant line. F of 27, that means cube root 27 and then square it. So the cube root 27 is 3, 3 squared is 9. And then if I plug in 1, I just get 1, so I got 8 over 26. I got 4 over 13. I'm going to set that equal to my derivative. Once I do that, I can cross multiply. 26 equals 12x to the 1/3, divide by 12, and I get x to the 1/3 equals 26 over 12, which would be 13/6, and then I would cube both sides. Okay, so that is the value. And that's going to be in my interval without computing it. It's a little more than 2. A little more than 2 cubed should be a bit more than 8, which is in there. Okay, so here is the curve sketch kind of problem without actually sketching. Critical number would be when the derivative is 0. That happens at x equals 3. So I break up my number line at that critical number, and then do some test points, right? So f prime of 0, f prime of 4, and I plug it into my derivative. That should be positive, that should be negative. So this function is going to decrease and increase, which we already know. This is an easy one. That's a quadratic function, it's a parabola, right? So it's increasing from 3 to infinity and decreasing from negative infinity to 3. Which means we have a relative minimum at 3 comma whatever you get when you plug in 3 there, and then there would be no max. Okay, same question, first derivative test. So f prime of x is denominator times derivative of the numerator minus numerator derivative of the denominator all over the denominator squared, and then up top I get x squared. This would be 2x squared plus 14x, so that should just be negative x squared minus 14x all over x to the 4th. Okay. When's that guy equals 0? Well, there's definitely a critical number at x equals 0. because that's when the derivative is undefined. And then the numerator is negative x squared minus 14x is what that says. And if you set that to, well, you could probably do something like that. We could clean this up. That's if I factor out a negative x out, and that would give me x plus 4, right? If you distribute that, you get negative x squared plus minus 14x. And then these guys, that'll cancel out with that. So really I can have a better looking simplified derivative at that. So I have a critical number at x equals 0, but also one at x equals negative 14. So it's increasing. Of course, you have an asymptote at x equals 0, right? So we'd have to break up the number line like this. Negative infinity to negative 14, negative 14 to 0, and then 0 to infinity. Take a test value from each of these intervals. And plug it into your derivative. Plug it into this guy, right? If you plug in negative 15, you get a negative in the bottom, you get a negative here, and you get this negative 1. So it's 3 negatives, gives you a negative. If you take negative 1, this will be positive, this will be negative, this will be negative. That's 2 negatives, so that's a positive. And if you plug in 1, you get a positive, and a negative. That's 1 negative. So this function is on this interval. This interval is going to decrease, and this interval is going to decrease. So those are my 2 decreasing intervals, and then this one would be increasing. So you got a minimum at negative 14 comma something, and a maximum at 0 comma, oh, that's not a maximum, sorry. You have no maximum, because it does increase up until x equals 0, and then after that it decreases, but that's a vertical asymptote on your graph, right? So that can't be a maximum. And then I'm just saving some time. Plug in negative 14 into this, and you'll get your minimum value. Okay, trig. So f prime inflection. So this is just asking about inflection points. We could ask about the first derivative, but let's just go right to the solve the question. F prime is 1 minus sine x. F double prime. So from this we could get intervals of increasing, decreasing, and max and mins. But the question is just asking for concavity, points of inflection. So I'm going to take the second derivative, which would be negative cosine x. And then if I set that to 0, negative cosine x equals 0. We know that the cosine equals 0 at pi over 2 and 3 pi over 2. Okay, so I would break, those are my possible inflection points, not critical numbers. Possible inflection points, that's where the second derivative is 0. So I could break up my given values for x at these 2 possible inflection values for x. And then test values for the second derivative. Pi over 4 is probably a good choice for this one. Pi is probably a good choice for this one. And we got a small interval here again. So I would say, what, 11 pi over 4? No, that's not what I meant. I meant 7, almost 2 pi, right? 7 pi over 4, that's in quadrant 3. So if I plug that into my second derivative, we got mind the negative here, right? Because when you plug in pi over 4, you get a positive value for cosine, but then you get the negative makes it negative. We plug in pi, you get negative 1. Negative makes it positive. And you plug in 7 pi over 4, you get a positive for cosine, because cosine is positive in quadrant 4, and then that makes it negative. Okay, so you're going to have a function that is concave down, then concave up, then concave down, right? That's what f double prime tells us about f, which means we got inflection points at pi over 2 and 3 pi over 2, pi over 2 and 3 pi over 2. If you plug those in, the cosine of pi over 2 is 0, cosine of 3 pi over 2 is 0, so you just end up with the same input as the output, right? Plug in pi over 2 plus cosine pi over 2 plus 0. Okay, and then to answer the intervals of concavity, concave down, this one, and then concave up, that one. Okay, so based on this information, pick the graph. F of -1 equals f of 5 equals 0. So that happens. That one looks okay. That one looks okay. These can't be either of these guys. They only have one x-intercept, so they're out. First derivative is 0 at 2 and 4. That means it's leveling off when x is 2. This one looks okay. This one looks okay. This one looks okay. This one looks okay. So those two are still in the running. How about this one? First derivative is positive for x less than 2. That means the function is increasing, which is what these are the graphs of, for x is less than 2. So this function is decreasing when x is less than 2. So he's out, and this function's increasing. So it's got to be this guy. We could check the other stuff. Is it concave down between 2 or less than 2 and greater than 3? Well, yep, concave down and then concave down. Now we can check all this, but it's definitely this guy. Okay, limits at infinity. So this one is easy. If x goes to infinity, that thing goes to 0. And if x goes to infinity, 6 doesn't go anywhere. So that would be 6. This guy is going to be, should be does not exist, right? Because this is blowing up. And this is like the horizontal asymptote question from pre-calc. If the degree of the denominator is bigger than the degree of the numerator, horizontal asymptote 0. If the degrees are the same at infinity, you get that guy, right? The ratio of the leading coefficients. All right, the other one I mentioned, at infinity, if the degree of the bottom is greater, then that's going to 0. And then the third case, if this is bigger, the numerator is higher degree, then it's just going to either go up or down to infinity. And it asks, I think it's just saying, we don't have to say if it's positive infinity or negative infinity, we just say does not exist. Okay, this guy, so this is similar to the rational functions. It's not a rational function because that's not a polynomial. But at infinity, really, we just got this divided by this, right? That doesn't really matter. And then at infinity, or at negative infinity, I should say, what happens with that guy? Well, you square the negative number, then you square root it. So that's positive. And it's really just a positive x, right? We don't have to worry about the plus or minus thing because we know it's just going back. So what happens here? That also is going to a positive value, right? So you end up with, because when you plug in really small negative numbers, this negative times this negative is a positive. So this is the ratio you end up with, and you get a positive 1/6.